Hi there, everybody. Today we're going to move into graded potentials. So we finished up talking about resting membrane potential, and then we talked about equilibrium potential and how much each of those ions, sodium or potassium, contributes to our resting membrane potential. Well, now we're going to transition into graded potentials, right? So we're going to start talking about how changes in resting membrane potential are used to receive and send information within our bodies. Like always, there is an accompanying worksheet along with an objective list and vocab that are up on Canvas. So you could take a minute here and find those before we move on. All right, first thing we're going to do is back up a bit and revisit the functional anatomy of a neuron. So we're going to look at the different sections or segments of the neuron and look at the physiologic events associated with each of those segments. We're then going to focus on the receptive segment that receives signals. It's receptive. And then we're going to describe the postsynaptic potential. All right, here we go. A couple of comics here related to neurons to kick us off. That's Trump up there in the top left, back from his Apprentice TV show days. Kind of timely given that the vice presidential debate was last night between Vance and Walz. And then who can forget the Kanye and Taylor incident there? I'm going to hide my face. No more camera anymore. It's kind of distracting probably for everybody. Here you can see we have just a stereotypical neuron. And we're going to go through the different segments here, starting at the far left in the segment we call the receptive segment. It's the receptive segment because it's receiving signals, right? So you can see that the receptive segment is both the dendrites as well as the neuron cell body, or the soma. So what we see happens here is we receive signal in the form of neurotransmitter, right? So there's neurotransmitter that's been released from a presynaptic neuron. So the neural body and dendrites that we're looking at here are part of the postsynaptic neuron. When these neurotransmitters bind chemically gated channels on the receptive segment, we're going to develop what we call a graded potential. Moving into the next segment then, we have what we call the initial segment. Right? This is sometimes also referred to as the trigger zone. That is because it is at this portion that all of those graded potentials that are generated within the receptive segment, they all kind of merge together here, and it determines whether we're going to kick off an action potential or not. If we hit the threshold that we need to get action potential, we fire an action potential, which is why it's sometimes called the trigger zone as well. This is also the axon hillock, if we're thinking back to our structural anatomy of the neuron. The next segment we call the conductive segment. It is along this segment where we have one-way propagation of action potential. We're going to see that voltage-gated channels open sequentially one after another as that signal progresses down the axon to the transmissive segment. Okay, so this includes our axon terminals here, and this is where we get action potential leading to the release of a neurotransmitter onto the next cell, right? Whether that is another neuron or muscle or a gland. All right, here we are zooming in on the area where the presynaptic neuron is synapsing with the postsynaptic neuron. Now notice that there are several presynaptic neurons that synapse onto the receptive segment of that postsynaptic neuron. If we zoom in on this area right here, this is what we're going to see. So we have these axon terminals of several presynaptic neurons. It's not a one-to-one relationship, right? And if we look inside of the axon terminals, we can see all these vesicles packed with neurotransmitter in each of these. So there's a synapse associated with each. Now, on our postsynaptic cell, we are going to have what we call chemically gated channels. And I'll represent those with a CG as we move forward. They're chemically gated, or synonymous with our ligand gated, because they bind chemical. And that chemical is the neurotransmitter that is released from the presynaptic neurons. Right? We're going to see that when neurotransmitter binds these chemically gated channels, they're going to allow ions to flow. Right? So these channels are going to be specific to cations or certain ions, and then we're going to allow those ions to move down their gradients. Right? Now, I want to back up here a second and just talk about the two kinds of potential changes we can see within a neuron. Okay, so the area we're going to focus on is going to be the receptive segment today, which we are going to be talking about developing these graded potentials. We're going to see that these graded potentials, they are just short distance signals that move through that soma of the neuron. It's a small current, and it dies off or diminishes over distance, right? Graded potentials can be generated from chemically or mechanically gated channels. Now, in contrast, right, so short distance, if anyone's ever done this string between two cups, my son was just asking about how it worked. We can compare graded potentials then to action potentials, which are different. These are long distance signals and larger currents, and these don't diminish as they move along the axon. They start at the trigger zone, and then it moves through the conducting and secretory regions of the neuron, and they're associated with the opening of voltage-gated channels, not chemically gated channels. Okay. So again, we are going to focus today on graded potentials and the receptive area of the neuron. Okay, a little bit more on graded potentials. Again, just to orient you, we are talking about the receptive segment right here, dendrites and soma. We say that graded potentials are the main event within the receptive segment of the neuron, meaning our goal here is to develop graded potentials. We're going to see that they can either be excitatory or inhibitory. And when these accumulate at the axon hillock, that'll determine whether we get action potential kickoff and propagation or not. Graded potentials we're going to see are typically less than 1 millivolt, so we say they're very small, and they are short-lived, right? They're ephemeral, and they only travel short distances, at least a single potential. There are changes to the resting membrane potential. So remember here, when we're talking about this neuron, we're talking about resting membrane potential, which we said is around negative 70 or so millivolts for your typical neuron. So graded potentials are going to be small deviations in our resting membrane potential, meaning we can either become more negative, which moves us away from action potential, or we could become slightly more positive, right, which is moving us toward action potential. Okay. So small deviations in our resting membrane potential. We can either depolarize or we can hyperpolarize. We're going to see that these changes to our resting membrane potential are going to be caused by movements of small amounts of ions. And these are going to be ions that you're previously familiar with, right? Like sodium ion. Now, it's going to be neurotransmitter that's released from your presynaptic neuron that binds receptors on the receptive segment of our postsynaptic neuron that open chemically gated channels, right? And then that's going to allow flux of those ions across the cell membrane. Let's pause here for a minute, and I'm going to take a second here to review the concepts that we've talked about so far with an illustration. So a couple of key things. When we draw out these neurons, we can draw them in a simplified manner so that we can see the other events more clearly, and it also takes us less time, right, to draw a neuron. So we're going to draw almost like a simplified stick figure. So we're going to represent the cell body, or the soma, with just a circle. Okay. The axon is going to be represented straight line, and then axon terminals just with this fork, right? Just a Y. So in reality, there would be dendrites coming off of this cell body. We're just assuming they're there. And then there would be far more axon terminals here at this end as well. But this is really all we need to get our point across. So we're going to say this is the second neuron in a chain, right? So this is going to be our postsynaptic neuron. So before that then, and I'll do a different color to indicate presynaptic. Let's say we have a axon, right? There'd be a cell body associated with that. And then here's the axon terminal of the presynaptic neuron. And remember, when we say presynaptic and postsynaptic, we're just referring to the position in that chain. So this is the synapse here. This one is before the synapse, so it's presynaptic. This neuron here is after the synapse, so it's postsynaptic. Okay? Now, let's say that the presynaptic neuron, and remember, we're just drawing one here for simplifying the purpose of this drawing, right? But in reality, there would be other presynaptic neurons synapsing onto this postsynaptic neuron. Okay. So let's say that this presynaptic neuron is releasing neurotransmitter. Okay, I'm just going to draw some chemicals here. These chemicals are neurotransmitter. And we're just going to be vague and just say it's neurotransmitter, not give them a name. Okay. Now, on your postsynaptic neuron, there could be receptors for that neurotransmitter. And these receptors here are what we call chemically gated channels. So I'm going to represent these as CG moving forward. So chemically gated channels. And remember, the chemical that they bind is neurotransmitter. So chemically gated just means they have to bind neurotransmitter before that gate opens or that channel opens. Right? So neurotransmitter can bind a receptor, which is a chemically gated channel. And I'm going to indicate neurotransmitter here, NT. So let's say neurotransmitter binds this chemically gated channel, and it leads to an influx of a positively charged ion. We're going to keep this vague as well. I'm going to draw this purple. So let's say there's some ions out here. They're positively charged. And when neurotransmitter binds this chemically gated channel, it opens, allowing this ion to move into our postsynaptic neuron. Now, I drew a positive charge here because we're assuming in this example that that ion is positively charged. Well, then we start to develop some graded potential, right? This positive charge is going to start moving along the inside of that cell, right? I'm just going to draw this little bouncing around. But remember, it only travels a small distance. These are graded potentials, and they diminish over distance and time. Okay, so let's say it fades out around here before it makes it over here to our axon hillock, which is our trigger zone. Right? In order to kick off an action potential, we're going to see we need multiple graded potentials to converge here at the trigger zone. Okay, so how do we do that? Well, in order to make it to that trigger zone, we're going to need more receptors for that neurotransmitter to be activated, more chemically gated channels to open. So I'm just drawing some additional receptors on our postsynaptic neuron here. Okay. So let's say that the neurotransmitter released from the presynaptic cell binds to these chemically gated channels. Right? They're the same type of chemically gated channel, so they're going to let in the same type of ion. So we're going to see influx of more of this positively charged ion into the cell. Well, that's more positive charge. Okay. I'm going to indicate those with some plus signs there. Also remember here that our resting membrane potential, our RMP of our typical neuron, is around -70 millivolts. And we talked about how we arrived at this negative 70 millivolts in the previous class, looking at the contributions of sodium and potassium. Okay. So our resting memory potential is negative 70 millivolts. Well, with this incoming positive charge, we start to depolarize a little bit with these graded potentials. Okay. So let's say we have these additional ions, positively charged ions moving in, and now we have enough reinforcement that we make it to the trigger zone. All right, so this is a depolarization that is reaching the trigger zone. We're becoming more positive. We're moving away from negative 70 and we're becoming less negative. So let's say we hit negative 55 millivolts then. So we're less negative because these graded potentials, these positive graded potentials made it to the trigger zone. Well, we're going to see that negative 55 millivolts is our threshold for action potential. Okay. And when we reach this threshold, it kicks off action potential at the trigger zone, or the axon hillock. And we'll see one-way propagation of signal in the form of an action potential move down that axon. Now, this is going to involve voltage-gated channels, not chemically gated like we saw out here in the receptive zone. And ultimately, we're going to see that that action potential is going to release neurotransmitter from the axon terminals of our postsynaptic neuron. And then these can go on and bind a muscle or another neuron in that chain, for example. So far, I've been intentionally vague, just saying chemically gated channels. Well, now I'm going to introduce the three possibilities of chemically gated channels that are found on our postsynaptic neurons. Okay, so first of all here, we could have a chemically gated cation channel. Okay, so remember, chemically gated just means a neurotransmitter is going to bind and open up that channel. Now, when we say cation, that just means a positively charged ion, and it's non-specific here, this channel. So what does that mean? It means that the overall effect when we open this channel is going to be an influx of sodium, which is positively charged, meaning that the internal environment of our neuron now, our postsynaptic neuron, is going to be a little less negative, right? Because it was at negative 70 millivolts for our resting memory potential, but now we have an incoming positively charged ion, so maybe it bumps it up to negative 65 millivolts. Okay, so we say that this is a chemically gated cation channel because the overall effect is sodium moving in. You need to remember that potassium is also a positively charged ion, so a little bit of potassium can leave. But the overall effect by far is the incoming sodium, which leads to a depolarization in that instance within the postsynaptic neuron. So I'm going to put dipole. Remember, that's becoming less negative, more positive. Okay. Next up, we have a chemically gated potassium channel. You might have some idea of where we're going with this, but if we open a chemically gated potassium channel, remember, these neurons are cells, so they have an actively running sodium-potassium pump. So we've been concentrating potassium inside of the cell. So then when we open a channel specific to potassium, it's going to move down its gradient, right? And we're going to see that potassium then is going to leave our cell. Well, if we have a positively charged ion leaving, that's going to make this internal environment a little more negative, right? So in this instance, we say we hyperpolarize. We become even more negative. So we move more negative from negative 70. Let's say maybe we go to negative 75 millivolts. So this is a hyperpolarization. More negative. Okay. Now finally, we can have a chemically gated chloride channel. Okay. So remember, with chloride, there's far more chloride outside of the cell than there is on the inside within the cytoplasm. So when we open a chemically gated chloride channel, negatively charged, it's going to move down its concentration gradient into the cell, again making this environment more negative. So this is another hyperpolarization. depolarization. Okay. Meaning we move further away from threshold. We're less likely to trigger an action potential. With these chemically gated cation channels, we are depolarizing the cell. We're becoming more positive, right? So we're moving from negative 70 and becoming less negative. And if we hit that negative 55, then that is our threshold and we will have action potential. We said that these graded potentials are short-lived, right? And they can only travel short distances. So why is that? Well, let's take a look at this illustration here. So you can see here we have a chemically gated channel. We can also see that it is a cation channel, right? Chemically gated cation, because we have an influx of positively charged ions. Okay, so this is a chemically gated cation channel. So it opened when this neurotransmitter here, indicated by this little triangle, bound this chemically gated cation channel. When this happens, it allows for an overall influx of sodium, right? So that's this positive charge that's moved in here. Now, why is the spread of this depolarization, this positive charge from sodium, only moving a short distance? Well, there are a couple reasons, right? When these channels open, the sodium moves inwards. But this isn't a hollow open space, right? There's cytosol within here, the fluid. And that acts as kind of, it forms some resistance as this ion tries to move through that fluid. Okay, so it only travels a short distance. And the other thing is, remember, we have leak channels specific to these ions, right? So let's say we have a leak channel here specific to sodium. Okay. Well, sodium then, in addition to experiencing that resistance from the cytosol, may also just leave our neuron again. Okay, so for this reason, we say that these are short-lived and travel short distances. The third characteristic of these graded potentials is that they vary in the degree of change and direction of change within the resting membrane potential. Okay, so what does that mean? Well, it means we can have responses of different magnitudes. So for example, let's say we bind a whole bunch of chemically gated cation channels, right, with neurotransmitter from the presynaptic neuron. Okay, well, that is going to lead to a bunch of depolarizing graded potentials, right? So maybe we bind one chemically gated channel. We get a small depolarization. Let's say we bind two, it's a little bit larger. Let's say we bind 3 chemically gated cation channels, and that depolarization makes it to the trigger zone, right? Well, here you can see we have a threshold for action potential at negative 50 in this example. So because we've reached negative 50 now, we've depolarized, this will kick off action potential at the axon hillock. Okay, so you can see here we had varying response due to how many chemically gated channels were open. Okay, so they can be large or small, these graded potentials, based on how many contributors you have. Okay, so we say that they are graded, right? That's where we get the graded. They can differ in their size. Let's say we have hyperpolarizing graded potentials, right? Which means becoming more negative. Well, let's say we bind one chemically gated chloride channel. Right, we get an influx of a negatively charged chloride, become more negative. Let's say we bind 2, so we bind 3. Well, now notice we're moving away from threshold and we're becoming more negative. So this is a hyperpolarization. Okay? So we can depolarize or we can hyperpolarize. And it's actually going to be the summation of all these events, all these graded potentials at the trigger zone or axon hillock that are going to determine whether we have action potential or not. Okay, just to clarify here, I want to briefly touch on depolarization, repolarization, and hyperpolarization again. So we said our neuron resting membrane potential is at negative 70 millivolts. This is our resting membrane potential. Okay. So if we depolarize, this means approaching 0. So we see this here, right? We're moving back towards 0. We're becoming more positive. This is a depolarization, right? We're not polarizing, which is moving further away from 0. We're depolarizing, moving closer to 0, okay? And we can also hyperpolarize, in which we move further away from 0, right? More away from 0. So becoming more negative, okay? In this instance, you're less likely to hit threshold, which is around negative 55 millivolts. Okay, so we're going to see it's depolarizations that lead to action potential and hyperpolarizations that lead away from action potential, less likely. Okay. Now we also have repolarization, which just means you return to your resting membrane potential after a polarization. Okay. I'm sorry, that's a return to resting potential after depolarization, this repolarization. Okay, so if we depolarize, become more positive or less negative, however you want to say it, well, if we return back to our resting membrane potential, that's a repolarization, right? Moving further away from 0. These changes to our resting memory potential in our postsynaptic cell that we've just been calling graded potentials so far, they actually can be directional, right? They can depolarize or hyperpolarize. So we term these postsynaptic potentials because it is potential, graded potential, that's developing within our postsynaptic neuron. Okay, so we define it as an alteration within our postsynaptic membrane due to receptor activation. Receptors just are chemically gated channels, right? So we said there are cation, we said there was potassium, and we said there was chloride, right? Those are our chemically gated channels. Okay. We also say that these postsynaptic potentials are graded, and I tried to explain before that just means they can vary in size, and that is due to the amount of neurotransmitter that is released by your presynaptic neuron, right? So if there is more neurotransmitter released from your presynaptic neuron that binds more chemically gated channels, well, then we're going to have greater changes in our resting membrane potential in our postsynaptic cell, right? So we're going to see greater alterations, I should say, deviations from our resting membrane potential in our postsynaptic cell. And these are directional, right? So far I've just been saying positive or negative. Well, we can call them excitatory or inhibitory. So let's take a look at these over here on these figures on the right. So here we just have time on our x-axis, and on our y-axis we have the membrane potential within our postsynaptic neuron, right? So here we are, here's negative 70, which is our resting membrane potential in our postsynaptic neuron. Now, if we have a depolarizing charge or ion moving into our postsynaptic cell, we say that is excitatory. It's excitatory because it is moving us closer, right? We can see one right here, to threshold at negative 55 or so. And once we hit that dashed line there, that's when we get action potential. Okay? So we term these excitatory postsynaptic potentials, and we're just going to refer to them as EPSPs from now on. Excitatory because it's moving us towards action potential, it's exciting the cell, and then it's postsynaptic potential. So we're just giving this a name now, these depolarizing graded potentials. Okay. Well, they can also be inhibitory, right? So excitatory would have been caused by opening of your chemically gated cation channel. That's going to lead to depolarization. Well, let's say we have activation of our chemically gated potassium or chloride channel. Well, that is going to lead to inhibition, right? Because we are moving further away from our negative 70 resting membrane potential. We are hyperpolarizing and becoming more negative. Right? So maybe we're at negative 80 now. And because of that, we're further away from threshold, aren't we? So we're less likely then to have action potential. We're less likely to hit this threshold at the axon hillock. And those are IPSPs, inhibitory postsynaptic potentials. I'm going to do another drawing here and just illustrate again the concepts that we've touched on so far. All right, here we have an illustration from your book showing something very similar to what we just drew. We can see there are many presynaptic neurons, which is more realistic than what we've been drawing, and they are releasing neurotransmitter. Okay, now that neurotransmitter is binding chemically gated cation channels in this example. And we know that the overall effect of binding these cation channels is an influx of sodium, right? And you can see here that that influx of sodium, that's going to generate EPSP, excitatory postsynaptic potentials. That's because we're approaching threshold, we're depolarizing and becoming less negative, approaching that negative 55 millivolts to kick off action potential, right? So you see this gradual spread of these EPSPs and that depolarization along the inside of the cell membrane. And again, if we get enough of these EPSPs that are reinforced along the way and they reach that axon hillock, that is going to give us action potential. In contrast then to our excitatory postsynaptic potentials, or EPSPs, we have these IPSPs, these inhibitory postsynaptic potentials, right? And we know they come in, well, it can be caused by two different chemically gated channels. Those include our chemically gated potassium channel and our chemically gated chloride channel. Either way, it's going to move us further away from our threshold of negative 55 millivolts for action potential, right? So let's say we open a chemically gated potassium channel. Well, we've been concentrating potassium inside of this cell with our sodium potassium pump. So potassium is going to leave. We're losing a positive charge, which makes our internal environment more negative, right? Or let's say we open a chemically gated chloride channel. Well, chloride, negatively charged, is concentrated outside the cell. So when we open a chemically gated channel specific to it, we have negative charges entering our neuron in the form of these negatively charged ions. So these generate IPSPs. These are inhibitory postsynaptic potentials. And they are moving us further away from threshold at negative 55 and hyperpolarizing our membrane. So we started at negative 70 millivolts. Well, maybe we're down at negative 80 millivolts now. We're less likely to have action potential. Okay, how about stick figure postsynaptic neuron here? And the axon terminals. Let's say we have a chemically gated cation channel here. Okay, and let's say there's some neurotransmitter that's released by the presynaptic neuron that binds this chemically gated channel. Okay, let's go ahead and zoom in on what's going on with our membrane potential then. Well, as before, we're going to illustrate our membrane, just the bilayer, and then we indicate which we're looking at here, the outside versus the inside, right? It's a little I there for inside. So this is a cytosol, and this is your extracellular fluid. Okay. And we have this chemically gated channel bound, I should say inserted into the membrane. And we said this was a chemically gated cation channel. So I'm just going to indicate that with a plus sign. Okay. So neurotransmitter was floating around out here, released from our presynaptic neuron, and it binds your chemically gated channel. Right. Now, because of our sodium-potassium pump, I'm going to just draw this over here, right? And we're going to say this is our sodium-potassium pump. So remember, that's primary active transport. We're using energy to move these ions in different directions. So we're going to move, with this, we're going to move potassium into our neuron. We're going to concentrate it there. So we're moving it against its gradient, right? And concentrating potassium inside the cell. Well, simultaneously then we are moving sodium out of our cell and concentrating it out here. Okay. When we bind this chemically gated cation channel, the overall effect is then sodium is able to move back down its concentration gradient into our neuron. Okay. So this is a positively charged ion. So our resting membrane potential is negative 70 millivolts. Well, now let's say we're a little bit less, right? Let's say this signal is reinforced along the way. So we'll have some other chemically gated cation channels that are being activated. Right? So that means we would have more of these opening out here. Chemically gated cation channels leading to a greater influx of sodium, which is positively charged. So this is a depolarization, which is moving us closer to threshold. So now let's say this depolarization is able to make it to the trigger zone. Right? It's not dying out because it's reinforced along the way by all these other chemically gated cation channels. So it reaches our trigger zone. And if that depolarization that reaches the trigger zone is large enough, if we are able to hit negative 55 millivolts at the axon hillock there, then we get action potential. And that signal propagates again down to your axon terminals, where we will lead to release of other neurotransmitters onto some type of effector cell. Well, our previous drawing showed a culmination or summation of excitatory postsynaptic potentials at the axon hillock, right? EPSPs. All of those were depolarizations. Let's take a look at the IPSPs then. So again, we have our neuron, and then let's say we have some different chemically gated channels here on this postsynaptic neuron. Let's just say that these are chemically gated potassium channels. Okay, so chemically gated potassium channels. So we're going to zoom in on this region like before, or that portion of the membrane. And like before, we'll just indicate that with a bilayer. And we have outside and we have inside. Okay. All right, so again, we had our sodium-potassium pump over here doing what it does, moving ions in different directions. So we've been moving and concentrating sodium outside of the membrane, simultaneously concentrating potassium inside our cell. Okay? So then we have these chemically gated potassium channels. There's our chemically gated potassium channel. And we're going to see that some neurotransmitter released by the presynaptic neuron binds this chemically gated potassium channel. So there it is. It's binding that channel. Now, when that happens, which way is potassium going to move? Well, it's going to move down its gradient. We've been concentrating it inside the cell, so it's going to move outward. What effect does a positively charged ion have when it leaves our cell? Well, it makes it more negative in here, right? We're losing a positive charge, okay? So if our resting membrane potential was at negative 70 millivolts, well, maybe now we're at negative 75 millivolts. So this is a IPSP. This is inhibitory postsynaptic potential. Right? And if we have enough of these chemically gated potassium channels, generating enough IPSPs, right? Well, then that negative effect is going to make it to our axon hillock, and we're going to be less likely to fire an action potential because we're farther away from threshold now. Now, in reality, you are both going to have IPSPs and EPSPs. So if we add in our other drawing, let's just say we have these chemically gated cation channels, right? So whereas our chemically gated potassium, we're hyperpolarizing. That's a negative charge. We now have these chemically gated cation channels that are leading to depolarizations, EPSPs, right? So small excitatory postsynaptic potentials. Okay. And let's say there's enough reinforcement that these make it to the axon hillock. Well, it's going to be the summation of all your IPSPs and your EPSPs that tell us whether we get action potential or not. I'm supposed to say AP there, right? Do we hit that negative 55 millivolt threshold? And it's going to be the culmination of all these EPSPs and IPSPs that tell us if we hit negative 55, then we get that action potential. Okay, so it's the summation that occurs there of IPSPs and EPSPs at the trigger zone or the axon hillock. Okay? So at rest then, resting membrane potential, our membrane looks something like this, right? Here's the outside of the cell, and here is the inside of our cell, the neuron. Okay. Remember that all of our unbalanced charges line up right at that cell membrane, right? And because we're negative 70 in here, we're more negative, it's going to be those negative charges that line up on the inside of the cell membrane and the positive that line up on the outside. Okay? Okay. If neurotransmitter, we can see here, neurotransmitter has bound this chemically gated channel. We also know it's a chemically gated cation channel because we're getting an influx of positively charged ions, and that's in the form of sodium. So that area that depolarizes due to these EPSPs, we call the active area. That's now depolarized due to these graded potentials. Okay. Now, the area is off to the side, right? It can move either way along that cell membrane, every way along that cell membrane, I guess, if we think about it. It's termed the inactive area at our resting membrane potential. That local current then, or that depolarization, flows between the active and the adjacent inactive areas, which results in depolarization of the previously inactive area. So in this way, then, that depolarization spreads a little away from its point of origin. But as we saw previously, this depolarization can only spread so far. It experiences resistance from the cytosol and it can leak out, right? Those ions have leak channels, and they can leave that neuron. So a good analogy here is to think of those graded potentials as spread by a passive current flow. So this is like the current within a wire, right? So they die over short distances because of that cytosol. Current leaks out. This is just like an uninsulated wire, right? This is why we insulate our wires so that that current doesn't leak out. Well, these leak channels are just like cause and effect like an uninsulated wire. Okay, so then we see the spread of that graded potential diminishes over space. This illustration right here is actually showing us just that, how at the initial site of change in potential, that depolarization, right, we're now at negative 55 instead of negative 70. Well, look at, we start to lose those positively charged ions through leak channels, right? And we then approach our normal resting memory potential as that signal dissipates away from that origin. So this is why we need reinforcement of other EPSPs or IPSPs in order to reach that axon hillock, right? Because we lose that signal as we move along. This figure is simply another way to look at that spread or that loss of those graded potentials as we move along the inside of that cell membrane. We are now going to focus on the initial segment of the neuron, right? And we said this is where we get the summation of all those graded potentials. All of your EPSPs and your IPSPs come together, and it determines whether we hit negative 55 millivolts to have action potential move down this axon. We call this culmination of your EPSPs and your IPSPs at the axon hillock, we call it summation, or we call it synaptic integration. We've said this a few times now, but the summation of your EPSPs and your IPSPs occur at that axon hillock or trigger zone. This is where all those voltage changes from the dendrites and soma of your postsynaptic neuron are added together. And that summation of those EPSPs and ISPAs are going to determine whether you reached threshold for membrane potential to initiate an action potential. So we think that the threshold then is the minimum voltage change required to have action potential. And we said this is oftentimes around negative 55 millivolts. Okay. In order to do this, we are going to need multiple EPSPs. Okay. Those need to reach that axon hillock together at the same time and add together to get action potential. So if we look at this figure here, we have time on our x-axis and then our voltage in millivolts on our y. So let's say we have a stimulus that is applied here just a little after 1 second. Well, you can see we had all these failed initiations at an action potential. And all that means is we had some EPSPs, but they did not bring us up to this negative 55 threshold. Those EPSPs, when they reached the axon hillock, were not enough to hit negative 55, so we did not have action potential. Okay. What happens once we do reach that negative 55 threshold? That's when we get a new type of channel opening that we call voltage gated channels. Right, so unlike chemically gated channels that respond to chemicals binding them, voltage gated channels respond to a change in voltage. And that change in voltage is usually around going from negative 70 to negative 55. Once that happens, these channels open and give us action potential. Moving away from our stick figure neuron drawings for a moment, we have a more realistic illustration of a postsynaptic neuron with all these presynaptic inputs from other neurons. Okay, so what we need to notice here with this illustration is, well, our postsynaptic neurons right in the middle, and then we have all these synapses from presynaptic neurons, and they're indicated with either a red axon terminal or a green. If it is red, that indicates that our postsynaptic neuron is receiving an inhibitory postsynaptic potential from that presynaptic neuron. Now, If that axon terminal of the presynaptic neuron is green, that indicates that we are generating an excitatory postsynaptic potential within our postsynaptic neuron. So I want to point out a few things here. You can see that these IPSPs, right, they're showing that these are moving along the inside of this postsynaptic membrane cell membrane. Okay. And then we have these EPSPs that are doing the same thing, right? So we're getting depolarizations inside from these EPSPs and hyperpolarizations from all these incoming IPSPs. Well, what happens is that all of these are added together here at the axon hillock, if those signals are able to make it, right? If those EPSPs and IPSPs are reinforced enough to make it to this trigger zone. Okay. If the balance is favored toward your excitatory postsynaptic potentials and the overall effect is a depolarization, and that depolarization allows us to move from that -70 up to -55, that's when we initiate action potential. We trigger the opening of those voltage-gated channels now. They respond to a depolarization, a change in voltage, and they open to initiate action potential. The last thing I want you to consider before we move on to the next slide is the relation of these synapses to the axon hillock. Right, so what do I mean? Well, let's say we are looking at these inputs right here, right? These synapses from a presynaptic neuron. So these are EPSPs. Notice they are located very close to the trigger zone. Well, that means they're more likely to make it to the trigger zone, right? So there is a spatial component. Now, the other thing is, let's say we get a IPSP and an EPSP that arrive at the axon hillock at the same time. If that happens, oftentimes we will get cancellation of those signals. So in addition to a spatial effect, there's also a temporal effect, right? The effect of time when they arrive at the axon hillock. Because of this, then, we have two types of summation that can occur. And those include spatial summation and temporal summation. And I think before I define these, I'm actually just going to show you an example of what these mean. Let's examine spatial versus temporal summation then. So first I want to start down here in the bottom left, right? And this shows the relationship of our postsynaptic neuron in relation to a few different presynaptic neurons. So you can see we have one input, it's excitatory, right? So that's going to lead to depolarization. And then we have another neuron that is also excitatory, shown in blue. So both these are going to lead to depolarizations. Then you can see we have one inhibitory presynaptic input, right? So that's going to lead to inhibitory postsynaptic signals, or IPSPs. In this first scenario here, let's say that excitatory input 1 fires, right? And we can see that up here. So it fires, and then a small amount of time passes, and then it fires again. Well, enough time has passed in between here that we return to resting membrane potential. So these signals that are being sent by excitatory 1 are reaching the axon hillock too far apart, right? So the signal dies off. This is where we're recording this potential that you see up here at the axon hillock. So you got signal 1 comes in, and then shortly behind it, signal 2 comes in from the same neuron. But they're not close enough together that they would add together at the trigger zone here. Well, let's say that they are fired in very close proximity then, right? So excitatory 1 fires, and then right after that it fires again very rapidly. Well, then both of these signals are going to reach the axon hillock around the same time. And if that happens, then we get what's called summation, okay? And because this has to do with time, the interval between the firing, that's where we get the temporal component. Temporal means time. So we call this temporal summation. And we define that then as multiple postsynaptic potentials, right? In this example, we're talking about EPSPs produced by one excitatory neuron, okay? if they're close enough together when they reach the axon hillock there, they sum together. So that's our first example of temporal summation. Well, now let's look at another example. Okay, so let's say we have excitatory input 1 fires, right? And so its signal travels down here to the axon hillock. Okay. Then let's say excitatory 2 neuron fires, and its signal eventually makes it to the axon hillock, but they arrive at different times. Well, in that instance, you can see here we do not have summation. Excitatory 1 makes it there, but not at the same time, so they're not adding together. But let's say then they arrive at the same time at the axon hillock. Well, then they add together, right? And we call that spatial summation. And that's defined as multiple postsynaptic potentials that are produced by multiple presynaptic neurons. If they are close enough together, when they reach the axon hillock, they sum together, right? And this is important because summation is how we hit threshold here, or negative 55, to give us action potential. That's what they're indicating here. The last thing I want you to consider would be an EPSP and an IPSP arriving together. So let's say our excitatory neuron 1, excitatory input 1, fires. That signal reaches the axon hillock or trigger zone. And then after some time, this inhibitory input fires. And that reaches the axon hillock a little bit later. Right? So this would be, this would look like this, right? There's your excitatory. We get a little blip there in a depolarization when it reaches the axon hillock, but it's not enough to hit threshold, right? And then sometime after, you get a little blip when that inhibitory reaches the axon hillock, but it is hyperpolarizing that signal, right? Because it is making the cell more negative. Well, let's say that both excitatory 1 and inhibitory 1 arrive at the same time now at the axon hillock. Well, in that example, you get what we call cancellation, right? And those two signals cancel out when they reach the axon hillock at the same time. Right? The last thing that I mentioned here is the distance to the axon hillock is important. Those inputs that are closer to the axon hillock, whether EPSPs or IPSPs, are more likely to reach the trigger zone or the axon hillock. The last concept I'm going to introduce today will be the concept of presynaptic inhibition or presynaptic facilitation. And I'm just going to draw this out for us quickly. Okay, last thing we're going to do is look at the relationship between presynaptic and postsynaptic neurons. I'm going to start with the example we've kind of been using throughout this entire lecture. Right? And we call this relationship axosomatic. Right, I'll try to write this out relatively quickly. Axosomatic. We got two parts to that word. The first is axo, meaning axon, and the last is somatic, referring to the soma. So we got axosomatic. And all that means is this is the relationship here. We have a postsynaptic neuron, and then we have a presynaptic neuron that synapses onto that postsynaptic neuron's cell body or dendrites. Right, so the relationship is axon terminal to soma, axosomatic. Okay, now This presynaptic neuron can lead to generation of EPSPs. Okay, so let's say it leads to a depolarization in this postsynaptic cell. Well, then we say that that is postsynaptic facilitation. So postsynaptic facilitation. Facilitation because it's helping us reach action potential in our postsynaptic cell, right? We're generating EPSPs in our postsynaptic cell because of the neurotransmitter this presynaptic neuron is releasing. Now you can also have the opposite relationship, right, which is a presynaptic neuron leading to IPSPs, right, which is hyperpolarizing this postsynaptic neuron, so it's less likely to hit action potential, and we would call that postsynaptic inhibition then, right? So postsynaptic inhibition, because it's inhibiting action potential in that postsynaptic cell. It's doing that because it is leading to generation of IPSPs, hyperpolarizing that neuron. So those are axosomatic relationships, but then we can also have a relationship called axo-axonal. Right? It's kind of hard to say. Axo-axonal. All right, so you can probably see where we're going here. We have axon to axon. All right, so what does that look like? We haven't looked at this one yet, but you could have this relationship here is also possible. All right, so we have our postsynaptic neuron, and then we could have a presynaptic neuron. Now this is called presynaptic facilitation, what I'm illustrating here. Presynaptic facilitation, right? Before it was postsynaptic facilitation. And that's because we can have another neuron here synapse onto the axon terminals of our presynaptic neuron. And with presynaptic facilitation, it's going to lead to an increase in excitatory neurotransmitter released from our presynaptic neuron. So we're more likely to generate EPSP in our postsynaptic cell, which means we're more likely to reach action potential. Okay. So the effect of this neuron here synapsing onto our presynaptic neuron is greater neurotransmitter release, leading to greater EPSP in our postsynaptic cell. Now, because this is happening before the synapse, this enhancement, we call it axo-axonal. It's axon to axon, and then it's presynaptic facilitation because it's before the synapse. Okay. Now we can also have another scenario in which a neuron synapses onto that presynaptic neuron, which inhibits neurotransmitter release. Right, so it's inhibiting neurotransmitter release, so we're less likely to have EPSP in this postsynaptic cell. Right? And we would call that then presynaptic inhibition. Presynaptic inhibition, because it's happening before the synapse, that inhibition, and again, it's an axon to axon relationship. All right, that is it. We'll see you guys next time.